Hello, everybody. I'm back again. It looks like I had a little time today to make two videos. Uh, I started showing you a problem related to the topic of statically indeterminate. You've seen a bunch of them, actually. If you look under the playlist for strength of materials on my page, you'll find a bunch of them actually with different forms. This is another example that I think is useful to take a look at. And it's it's a practical problem because, you'll see things like this in, structures, combination of concrete and steel. For reinforcement. So here we have a steel pipe, which is filled with concrete. So inside is concrete and the outside is made of steel, subjected to a compressive load of 80 kilonewtons, right? We want to find the average normal stress, sigma average, for the concrete and the average normal stress for steel, okay, due to this loading. So the question is, how much of this 80 kilonewtons actually belongs to steel and how much of it belongs to concrete? Now you have to understand that the way this load is showing here, acting right at the middle of the concrete, you feel as if the load is only acting on the concrete. Imagine if you cap the top and you apply a load, right? So you have a circular cap on the top and you apply a load, and that load actually is moving everything uniformly. So don't think just in terms of the concrete. That load is kind of distributed evenly on the steel pipe as well as the concrete, okay? So by the way, we have the dimensions. We have an 80 millimeter outside diameter and a 70 millimeter inside diameter. So if this is the steel, if you look at the cross section of the steel, if you look at the top view, for example, this is what you see. The outside diameter is 80 and the inside diameter is 70 millimeters, and inside you have the concrete right here. Okay, and then the modulus of elasticity of the steel is 200 gigapascal and the concrete is 24 gigapascal. Of course, you have to put concrete in compression because concrete is really lousy in tension. So that's why the load is a compressive load. And the length of the pipe is 500 millimeters. This is also, guys, an statically indeterminate problem. You see, if you look at a free body diagram of this, you see there is a load due to steel, call it F of steel, and there is a load that is in the concrete. I just call it F sub C for concrete and F sub S for steel. So one obvious equation is balancing the forces in the direction of the load. So F sub S plus F sub C must be equal to 80 kilonewtons. So there is one equation, right? But there are two unknowns. So the question is, where do you get the additional equation? If you remember from the other statically determinate problems that I've showed you in the past, again, if you look at the playlist in the strength of materials, just search for statically indeterminate and you'll see a few of them with different, approach used to solve them. You notice that what's really going to apply in this case is that when this the load that is acting, in the compressive direction, and as I say, is distributed, the whole thing is going to go down or is going to deform, which means that the deformation of the steel is going to be the same as the deformation of the concrete. So if it's like 2 millimeters, it goes down. That's for both the steel and the concrete. All right, so now you know that delta is what? Elastic deformation for axially loaded member is F times L divided by EA. So for the steel is F of the steel times the length of the steel. Now, of course, both of them have the same length, so I'm not going to even put a subscript. But look, I have to put a subscript for E and the area. Their area is different. So that's equal to what? F of concrete length is the same and it's going to get canceled, right? But of course, they have different material and different area. So let's go ahead and plug in, see what do we get. Oops, didn't want that to happen. All right. So look, guys, F sub S. Now, remember, this is just ratio. So this for this steel, we have 200 gigapascal. So I'll just put 200 because the 10 to the 9 is going to get canceled. Similarly, for the concrete, we have 24 gigapascal. Again, if I put 10 to the 9, it's going to get canceled. And similarly, the area of a steel is what? Pi over 4 outside diameter squared minus inside diameter squared. Remember, that's a pipe. And for the concrete, since the concrete is inside, it's just pi over 470. Again, the unit is not important, and the pi over 4 is going to get canceled. So I'll just put here for a steel 80 squared minus 70 squared in the denominator, right? And over here, I just put 70 squared. As I said, the pi over 4 is going to get canceled. Doesn't matter if I change the millimeters to meters. It's just a ratio. Guess what, guys? If you do the calculation, cross multiplication, force in the steel is going to be 2.551 times larger than force in the concrete. So this is going to be your second equation. If I call this equation 1, this would be equation 2. And where did this come from? It came from, again, the geometry and the deformation. So go ahead, replace f of s by 2.551 of f of concrete and solve for them. And once you solve for them, looks like f of steel is going to come out to be 57.74 kilonewtons. And obviously, f of concrete has to be what's left over from 80, because remember, the sum has to be what? 80 kilonewtons. So this is going to be 22.53. Sorry, 22. This is 47. Sorry, I just said 74. 47. So this is 53 kilonewtons. So you see the sum is 80. And then the next item is what? Figuring out the average normal stress. So the average normal stress for the concrete is going to be what? The force in the concrete, which is 22.53 kilonewtons. So just now put the appropriate units and look at the area. Now I have to worry about changing the millimeters to meters. Actually, let's write it as meters and square it. So you get Newton per millimeter squared. If you do the calculation, sigma in concrete should be not much, 5.85 megapascal. And then similarly, sigma in the steel pipe, the force, again, kilonewton has to be converted to newtons, right? And remember, the area is that, of course, the unit has to be adjusted. 0.08 squared minus 0.07 squared. Of course, that's going to be meters squared eventually. And if you do the calculation here, you should get about 48.8 megapascal. Okay, so I wanted to show you this other really simple problem, statically indeterminate problem, to go along with the other problems that I've shown you. Again, as always, thank you for watching and listening. And if you like the video, please subscribe. And I will make more videos for you. Have a good day and see you soon.